Please. Yeah, so to try to say a little bit about where we were yesterday, John. So here's the model. So we're talking about the standard model, NBL standard model. Random fields are distributed between minus W and W. And then here's the phase diagram, and I was talking various aspects of this. So the NBL phase is over here. And one of the messages is NBL is very fragile. NBL is some kind of quantum coherence, and thermalization is decoherence. And when decoherence meets coherence, who usually wins? Decoherence, right? And so having the coherence survive in some competition with decoherence, this is hard, right? For quantum experimentalists know this. And so that's part of the story here. So this, right? And so you have this NBL, and the question is, what kinds of it's fragile, it's unstable, decoherence, and what kind of instabilities does it have, right? And so there's one instability that we know about, which is the avalanche, and now we've realized, oh, that instability happens here. So this whole regime here, which looks NBL to numerics, ultimately it's going to be unstable to the avalanche, or maybe to something else first. Right? So this avalanche is one instability. We know it happens by here, but it might not be the first instability that happens. So a big question is, over here, which is physically more relevant, and maybe we'll actually access this regime by some method. What's the first instability that's going to happen there, or can we see the precursor of that? Right. So basically, by doing the analysis over here, I didn't actually see the avalanche instability. I had a bunch of theory of the avalanche instability, and we did a calculation which sort of anticipated, saw where this will happen. You didn't actually see it happen. You just said, over here, this system ultimately will be unstable to the avalanche within a calculation, but you don't actually see it happen. But here's the actual instability, the thermalization being seen is this process. And what's happening here, as far as we understand it, from this side, the dominant thing is the proliferation of the. And then if we go back a little bit back here, where we don't see the many body resonance proliferating, can we learn something about what is going to be the first instability as we take these systems larger out? Right? And might there be, is it going to be proliferation of many body resonances, or probably it's not going to be the avalanche? Is the important thing. So that's sort of the, that's to me the important open question to be addressed in advancing the theory of NBL further than where we are right now. Yeah. It can sharpen to a phase transition and go all the way back to here and be the phase transition. Yeah. Presumably not, because this whole region is unstable to the avalanche instability in itself. So how would we have phase transition in the middle of the thermal? Because what's the phase transition going to be? It's a phase transition with thermalization and not thermal. So I don't think that makes sense. Yeah. Exponential in what? No, but okay, so I didn't say it, but the avalanche instability is thermalization in a time that's not exponential inside the system. It's thermalization in the system. So if we take the infinite, I didn't do this argument. So if we take the infinite system and we look for these rare regions, they have some density. So they're spaced by some amount, right? The avalanche from this guy and the avalanche from this guy, and it's gonna, eventually they're going to overrun each other, and the whole system's going to thermalize, and that's going to happen in the infinite system at some time scale, which is exponentially large on some parameter, but it's not the size of the system. See what I mean? Yeah. Yeah. So I think the avalanche argument says the thermalization comment over here in the infinite system, it's fun. It's just extremely fun. And actually, so this is sort of where we were, and now I started talking about many body resonances, and I'll continue to that, but just in terms of the general picture I developed yesterday, other than the issues of many body resonances, is there any that anybody wants to ask about? All right. Great idea. Yeah. That's a great idea. Who's gonna do it? Well, he was at dinner too, right? You know, let's leave the dinner conversation out of it. Leo very kindly took all of the organizers and speakers out to dinner last. Where you guys were eating. What? Don't rub it in. But he's going to give you guys a nice. No, he's going to give you a nice dinner, different than the C4C on Friday night, right? So. Yeah. I'm going to get to that, and if I don't get to that, like I said, you go to. There you go. Go to Huse's poster tonight. But I think I'm gonna get to that. At least an abstract of his poster. Okay, so in this paper, Morningstar et al. So a lot of the work I'm talking about is in the paper. We did some sets of survey of many body resonances, and I'll tell you a little bit about how I started telling you a little bit about that last time, and let me continue. So what we did is we considered systems with lengths L closed now. So this is not the avalanche part of the argument, but studying the resonances. So we have a closed system. Just exactly diagonalize it, get the eigenstates, look at adjacent eigenstates in energy, ask, are they, so we look at a pair of eigenstates, alpha, beta. Now, eigenstate with that Hamiltonian and particular realization. Of course, we have to do many realizations to get statistics, but although actually we really don't. That's one of the things we learned is individual samples, when they're large, you look over all eigenstates, the different samples have pretty much the same statistics. As actually, if you're talking about resonances, these many body resonances, the statistics don't actually differ that much between samples. They actually differ between states in the same sample. Right? There's a lot of variation within one sample, and that's most of the variation, not so much between samples. So each sample is kind of typical. That's one of the things we learned. So anyways, we get state, now they're adjacent in energy, and then we ask, could this pair of states have between them an end-to-end resonance, right? And that means the expectation value first spin is of opposite sign in these two states, and the expectation of the last spin is opposite sign in these two states, right? And that's we call end-to-end either resonance or near resonance. Because it might be that the coupling is weak enough so that you wouldn't really call it a resonance. But they're adjacent in energy, so at least it's a near resonance. Okay? just to fix, because a lot of short range resonances. And we're interested, we're interested in, let's say here, so basically we got this regime and we're trying to understand the low energy, long time, large length scale physics. So we want to focus on large length scales, small energies. Right. There's a lot going on. There's a lot going on shorter scales. There's a lot of short scale resonances are much more common than long scale resonances. And so if you start looking at those, you just get lost in the weeds. No, they're just, it's just resonances that don't thermalize the system that are happening, and there's a lot going on, right? So these states here, right, J isn't zero, and there's a lot of short scale stuff going on. And I just don't want to get distracted. That's high energy physics. We're interested. Love it. Okay. And so then take this pair, as I told you, just look at the Hilbert space of this pair. Data. And then, if there is if these two eigenstates were involved in a resonance, that means each of them is a linear combination of more localized states, right? And so we look on this Coulomb sphere and ask, is there an A, B that are more localized than alpha and beta, and more localized? Our diagnostic is just, are the spins more polarized? Because A and B are the most polarized points on the sphere, then the polarization will be less in alpha and beta because you've mixed A and B and they have different polarization. So, and since it's just one plot sphere, it's just you can just formulate that as solving a quadratic equation. And so we can do that. And then just a second. And so then, as I said, in this space is A, B, we find our Hamiltonian, which is now HAA, HB, R. With this, where everything real. We also did a model variant. And so now here we can, now we know how to, this is just such a familiar problem. If this is comparable to these differences, then the eigenstates really are resonances. And they're sort of Schrödinger cat-like linear combinations of two. Right, A and B differ a lot over the whole sample. And right, if A and B are over here near the equator, then these are Schrödinger cat-like states, which are localized to two very different patterns, sort of bi-local. But more common, HAB is small compared to these energy difference, and then we're just dealing with a near. Yeah. And as Frank said, you could, rather than do it on the polarization, you could do it on the entanglement. But the polarization is the simplest thing to work with, one-side operators, and that did a good job for us. So that's right. Like I said, working in this regime, and we think by looking at this, we are studying, we're doing point of view of Kinetics matter physics. You want to ask what are the slow modes in this phase? What's the long length scale physics, right? And we think that it's these that are the dominant thing that's giving some activity, something going on in that regime. Right? Now, maybe there's something else also interesting that one could look at it, but this is interesting. It's definitely part or maybe all of the low energy physics of this regime. I'm insisting it's the most. There might be something else we missed. Not aware of. Okay. Right. Okay. So we is HAG, is broadly distributed. And that's said earlier, within each sample. We can do this for samples. We want to do a lot of samples. We don't do such big. We're going up the side. Within each sample, and that the state differences within each sample are a lot bigger than the sample differences of these distributed. So you get. You do big samples, you can go too deep. This edge gets cut off by numerical roundout error. So this stuff we mostly. And this is broad, like 3/4 magnitude. Really. And then you compare different samples, you know, it might shift a little bit, but it's not really that different. And now so then we could take the median, that's what I'll call typical, or we could take the maximum, the strongest resonance in that sample. And these are very good. Discovered very broad distributions with just roughly linear in L. Of course, maybe you can't do much of a range of L, so I would take that seriously. Very broad distributions, big difference between maximum resonance and typical, and then most of this variation is within one sample, not samples. These are all sort of big observations that seem interesting and relevant. And then, again, roughly speaking, this crossover is when this typical becomes comparable to the typical levels, right? And then you're going to have a lot of it. And as I'll say later, this maximum is a key actor in propagation of that apple. And the difference between this and this is one of the big ingredients that goes into making this big. This is this thing. It's this fist, right? This, because it's the very strongest resonance, it's producing more of an instability than this thing. Yeah. Not that we notice. Probability distribution of this difference is just a simple experiment. Right. No, that's a comment that's not answering your question at all. It's just a piece of information that came out of my brain and my mouth. Triggered by your question, but not answering your question. Yeah, but we did look for correlations. It's actually surprising. You can ask, oh, let's also look at pairs of states that are actually pretty far apart now. And the HAB has surprisingly weak dependence on the energy, even when we So many level spaces away, many level spaces away. So there's no strong correlation. We did look, nothing strong. We weren't looking for weak correlations, so they probably are there, but that's sort of where. One of the points here is we just did a survey of this. There's a lot to do here, and it's new, and hoping there'll be follow-up and more will be. Now, right. So as I said, so there's typical, the logarithm of HAB, we expect it to be, what? No, we expect here typical. So we would have C typical. So as I was arguing yesterday, which should go naively something like this, you know. It's make an estimate of it. Of course, it's going to depend on if this is going to. So the idea is this is. And then this guy here. Next. Sample. Maximum within a sample, mean over sample. Always better. And then what we find is typical. Here's well, certainly less than C max, and the difference is such that it may be it's consistent with it remaining different as you take L. Of course, we only took L from 6 to 16. So it's a big extrapolation. I don't trust it necessarily. Now, you know, one of the questions, which is, you know, really this is the typical of L, C max of L, and as we go to different sizes, they likely flow. Remember, I told you when we were estimating the avalanche, it was very clear, right? I made the semi-log plot, and there was a curvature, and here we had this thing, K of L, that I was talking about, and the critical value was 4, and it was flowing with L, right? And that's why this, as I go to larger L, this flows that way, and that's why this is only an upper bound of the active transition. Right? Now, here, we have looked for some curvature not very seriously and haven't systematically found a strong curvature. So I was expecting the curvatures we saw here would apply to the whole region. I was thinking, oh, this is a universal thing and I'll see it everywhere. But then we took some look at this stuff and the curvature seems to be weaker. So the first question is, you know, do they flow? And if so, what's the underlying mechanism? But these are open questions here. I'm talking about open questions for research on this direction. And then, you know, my vague idea of what might underlie the physics here, which produce the flow, which might really tell you how you expect this crossover to continue moving down like that, is that large-scale resonances are built out of multiple small-scale resonances, and as you put them together and do that, these things be constant. They flow in some way, right? And once it develops such a theory and how they flow, then make some sort of theory of what's going on up here. But that's just so that's. Done, but just my dream. Something might do. Maybe it's not the right direction. That's So that's just sort of an overview of what we learned about anybody. What are anybody resonances and how are we looking at them and what have we learned? And at least for sort of nominally a regime like here. And now what I'm going to do next is go down and ask about resonance's role in the avalanche. But before I do that, let me pause and see if there's any questions about what I've said so far today. Okay. Okay, so now I'm going to give Sue's going to give a very short abstract of his poster, or maybe Leo, when you do the abstracts of the poster, maybe he doesn't even have to give one because I'm going to give his right now. so that's up to you guys. Right, gives you 2 more minutes, or you guys two less minutes to sit and listen, because you know it's now the poster that's been advertised by far the most, and so maybe I don't know. Okay, so this is right. It's not only a poster, but very recently it's a URL. Also involved. Great. And this is about the role of resonances, actually I should say near resonances. This is sort of in violation of what I was saying, is that we shouldn't spend all our time focused on the avalanche because it corresponds to such ridiculously long time scales here. But remember how we were studying the avalanche? We have this map. Here's the system. Well, then have the system. Now, let's first not couple it to the bath, diagonalize it, find the eigenstate. Very weakly couple it to the bath. We can, if we take the limit of weak coupling to a system with non-degenerate eigenstates, and this is a Copian bath, that just produces a stochastic process just popping between eigenstates. You get a dynamic, but it's just a random walk among eigenstates with certain popping. That's what you get in this. So now, if you ask about the avalanche, what you do is you look find the slope of the function. We've diagonalized the system, we've got the eigenstates. Now, in terms of the eigenstates, we write out the Lagrangian problem. Actually, we really did ambiguous on this paper here. We only looked at a Floquet system. So it's actually a Floquet version. We didn't do the standard model. But I'm 99.99% certain that if we did it for the standard model, everything would be good. But we didn't actually split up. So that's actually a good problem. We didn't do the standard model. We didn't compare, and so that's a problem. Well, case system was intended. Yeah. Yeah, you have one site operators that are random field, random gates, the one site gates that do a random rotation about the z-axis. That's the random field, and then so in the Floquet model we just have one site gates that rotate about the z by a random angle, and then we have the 2 site gates are just GUE random. They're not Haar random because we want them to be weak, so they are a GUE Hamiltonian with a very. Or a GU one way of saying it is you just take a GUE Hamiltonian for 2 qubits, and then adjust the time that it acts, right? And a very small time corresponds to a very weak coupling, right? And then longer time. So you can say, we're just changing the time that we turn on the gate to make it interact more or less. So that's the Floquet system, and then you can make Floquet versions of it. Let's not go. Yeah. Well, we're not actually doing that. We're diagonalizing the Lombardian and finding its slowest mode. But it's equivalent. And then so we find this slowest mode. And what the slowest mode looks like, the first approximation is, so here's the set of eigenstates. And here's all the eigenstates with this spin up. And here's all the eigenstates with this spin down. Right? And then what happens, if you ask, how does that relax? What you find is there's a very small number of pairs of eigenstates where, so let's say we polarized it with more population here and less population here. Okay. It's going to equilibrate among these very quickly and among these very quickly. And there's a slow mode, which is going from here to here. And almost all that, a large fraction of that probability current going from here to here to relax this to 50-50 is happening between, there's different cases, but it's basically, there's I've ordered two pairs of eigenstates, one here and one here. And these currents, as opposed to these currents over here, right? Of course, I've ordered 2 to the L states here and 2 to the L states here. So we have 4 to the L states you could have current. And almost all the probability current is carried, not almost all, but order 1 fraction of all the probability current is carried by an order 1 number of pairs, right? Typically 2. Do I have that all right? Yeah, please correct me if I say something wrong. Sometimes correct, sometimes, but sometimes just right. And now remember, now we're working over near here. Yeah, we're deeper. And then you right. And these are strong currents because they involve the strongest resonance. Although the strongest resonance isn't necessarily this, it might be this one is a very strong resonance, and that makes this current strong by a mechanism that's not entirely obvious, but we figured it out. So there's like it's usually a set of 4 eigenstates, 2 here and 2 here. There's 1 resonance, and that makes 2 or 3 of the currents strong. That's really the picture. And if you want to hear more about that, it took quite a while. And so what we found is that the avalanche, the mechanism by which the avalanche spread, now we're asking, this is decaying at rate gamma of L, right? And that's going down exponentially, roughly like 4 to the minus L when we do the transition. But now we're asking, what sets this rate? What's the underlying physics setting this rate? And what's happening is this band, right? So now if we're relaxing this spin, right? The spin before it, right? Of course, as I said before, the slowest mode may not be completely on the last spin, but let's pretend it is. Let's pretend everything's just nice and neat going 4 to the minus, right? It's not, they're not perfectly in order, but let's pretend they're in order, right? And so the next spin before it relaxes 4 times faster. And so that means there's a time scale between these 2 relaxation times when all this stuff is equilibrated. And this guy is, right? And so that means all this stuff is cycling through all these eigenstates, right? Right. And so if this has all equilibrated, but this hasn't, that means you're up here and you've equilibrated amongst all these. And so that means you're going to visit a special, right? And when you visit the special one, now you have a probability of going down. When you're over here, your probability of going down is negative. So basically, the way the avalanche goes is it's thermalized out to a given point. It's state. It's the jackpot, right? It's the jackpot. Now I'm ending on a good state. It's a very special item. And now it thermalizes this all this, and there's some different jackpot that happens with a configuration here. And then so that seems to be the way the avalanche spread. Thermalizes this rather well. Goes to a very special state that collapses into the right. So that's what we learned. This driven by the very rare eigenstates, the strongest resonances, the strongest. So that means the avalanche spreads in a way that involves strong, typical and kind of perturbation. This is very specific to a particular sample with a particular amplitude. So if I added a perturbation, it would all be a range. We didn't look at that. No, this is the behavior of the system plus the back. It's just a no, this is a strong resonance in the closed system, and the bath is exploiting. Yeah. If you coupled it only infinitesimally, so it would be surprising if it. Now, we have not tested whether if we turn up this coupling strong, does this rearrange significantly? That's good. Yeah. Yeah, no, that's a very good question. We didn't test that up. Right? Always because the problem is in the numerics that if it's weak, you only have to deal with the diagonals. When you make it strong, the Hilbert space goes from 2 to the L to 40. So it's of course we could look at that in smaller systems. Yeah. 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 Right, but the key is the rates are falling off very strongly. So it will be sequential. Yeah, and it's not strictly sequential. There's order 1 deviations from staying in the book. So that people are fighting it. I prefer to make this a simple calculation. This is an infinite path with 0 level. There's no level spacing of that. That physics isn't included. So this is an avalanche model which would never stop. You're only asking how fast it's going. Other people have done studies where they actually put a finite buffer. Makes it more confusing. They sort of wanted to remove that. We wanted to look at the question, where there's few moving parts as possible, right? And so we said, oh, let's just take the limit of the infinite bath. We're only going to look at the spreading of the avalanche. We're not going to ask about it starting. We're not going to ask about it stopping. But we're going to ask about spreading, right? And so by making that simpler, the question simpler, you can make the model simpler, you can get really nice data. Studies with the model with a finite bath, it's just not as nice data. Well, that's the same. Yes, it is. Right. No, the math is really very far away from that. And it's been falling out that. And we just and of course, once it's coupled to spin one, it's coupled to the others through this system. But it's absolutely essential. Only if we're talking about a localized system with a vast population, right? Yeah. Yeah. Two given and order one fraction of the relaxation, which is striking, right? But it's sleep. So there's the strongest resonance here. Now we haven't really looked at. There's the strongest resonance, and then there's the next strongest resonance in that sample. So did we ever look at this? But those might have substantially different couplings. This is very broad. And so this first thing out here in this sample is empty dome. That's right. That's what we and so you've got it's a fun example. Here we're talking about in the sample. So there's a bunch of points here, and this scale is so this is much faster than this. This is much faster than this. And so sum up all these things, of which there's so many, but it turns out the sum's still dominated by the learned, not dominated, but the first few, or even the last one, gives order one fraction of all the relaxation. But these are now, so it's now the resonance. Right? And one resonance, because of some details which we understand, and I don't want to tell you about, about one resonance can facilitate 2 or 3 strong relaxation processes through things that are not simple to in a few minutes for me. But then the striking thing is to find that it just one resonance gives here, just that one resonance can dominate the large collection. I think it really all this is too happens in a lot of disorder physics is you have tails of distributions dominating the behavior. No, I don't think we understand. So way out in the distribution. Yeah, that might be the, the basic ingredient. Good point. If we formulate that in a well-defined way that. Oh, no, that we see, right? This is the typical picture. So you get this lowest load. And it's a state, it's an eigenstate of the Lagrangian, right, in terms of the eigenstate. And it's a positive amplitude. That mode would be positive amplitude here, negative amplitude. And this is typically what it looks like. Now, when tensions are involved, right? So you can have up, 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 down, down, up, down, down, and both is and it breaks up. Right, that happens some practice. I don't. Have we ever seen it break up into 8 groups? Yeah. Yeah, the slowest mode is it's either the end spin or some combination of the end spin. Well, okay, so there's the eigenstates of the Lagrangian and the eigenstates of the closed system. We have to be careful. Yeah, every eigenstate has this spin and this spin, either up or down. Right? And the simplest case is it breaks up into 2 groups, most predominantly on the end spin. And these eigenstates all have the end spin polarized up, and these all have it polarized down. And the relaxation in here doesn't have to put the end spin, so it's a lot faster than the process doing a random walk here with rates that are very different for all the different processes. The processes that involve shorter range resonances, so of course they're faster. And then the processes here are and the other thing we noticed is, so let me just add one more thing. This resonance isn't necessarily end to end. What we find is that it goes within distance one of this end, but it sometimes stops, maybe 75% of the way back to the beginning or 85% back to the beginning. So the process coupling the back to this spin seems like it can sort of tunnel over a distance of order, say L/5, and then it couples with resonance. That's not the full end to end, but it's like 85%. We know a lot about it. So that's where we are on that. Okay. 41 minutes. And so I have the topic. But before I leave MBL, go to so does the other model. One nice thing about the Floquet, no density. All the states are occupied on circle. Essentially, you almost uniform. You know exactly. That's one version. Care about the density of states, and you want to care about things. You don't have to do numerics to get the density. That's one small advantage. But so far in comparing with Floquet models, Indian models, other than the obvious things, one defensive observation, one doesn't, but those don't seem to have big consequences. So or just my feeling is MBL is not about transport. It's there and it's without transport. So you shouldn't, it's a hard problem. If you have a hard problem, study only its end, address it with more. Right? That's the reason. But whether that's just it may not be important thing actually, those extra features this model doesn't have. All yeah. Yeah. I think it's reasonable to think that the very small J, it is consistent K faster than 4 to the minus F. Just think about it in perturbation theory. K exponentially as something times J to the minus L. K arbitrarily small should be able to make J less than 1/4. So the naive argument is it's exponential. So why wouldn't the exponential make the not the exponential? But if it is exponential, turn down J far enough, it'll decay fast enough. So we'll have to stay. Yeah. That's some sense the argument. If there's a reason for this exponential stretch and not the simple exponential, right? If we have this thing not strict exponential without some power less than 1, then the LJ had a mechanism where not how can it 40/6? Actually, 40. But in fact, it's small. That's not clear. You understand, yes, why that is. Price. Found, but once you really started looking inside this, I might see. Okay. Last. Floquet system, no MBL, chaotic system. Lots of people have worked on this, so. Remember, now we're like the periodically driven system. People are very interested in this because a lot of experimentalists are by periodically driving your system, you can do all sorts of nice tricks that are hard to do in a time-independent Hamiltonian, or harder to do in a time-independent Hamiltonian. We want to lab with and period now. Omega. Right. And let's say our system without the drive is already chaotically thermalized. So say we had a Hamiltonian undriven, it's chaotic and thermalizing. Now we drive it periodically to turn it into something else, and we want to have it. So the total here, the only issue is, do we have an extensive conserved energy or not? A quanta omega what about this, right? So we have this drive. Drive really is a bunch of photons. The classical photons. So the system can get photons from the drive, go up energy by omega, or down. And really, we're asking, what kind of regimes of behavior can you have about this? Okay. Now, quantum energy at rate. So let's say gamma is the rate at which the energy is going. Sometimes you're at low temperatures and it's only absorbing photons. Or maybe you're up to your infinite temperature and it's close to the infinite. So let's say the higher rate. That's what it is. And then we have the Floquet operator, unitary Floquet operator gets to one period is well approximated by some effective Hamiltonian times the period. And so this will give all the dynamics of the system except this process. Okay. The difference between the full Floquet operator and this is the process of the drum. If the here in this one. And then this age effective, this is a quasi-local Hamiltonian, meaning quasi-local, meaning it might have terms that are high order in the degrees of freedom, but the total weight in this Hamiltonian due to the high order term is exponentially small in the order compared to the one or two. Quasi-local dominated by Huse spin term, but it's got its this H that that's how to do this systematically. You don't need to know general case. One can do Magnus expansion at high frequency where you generate such a thing systematically, but that's an asymptotic expansion, right? And if you're not in the regime where that occurs as well, we don't really know how to best approximate this. So let's just assume this doesn't. Not claiming I don't have fun. But if there's conservation law, will have consequences even if I don't follow. Yeah, but that's just an additive constant. Additive constant in Newtonian are not physical. No topology. There's all sorts of topological things in Floquet systems I know nothing about. I'm not going to tell you anything about it. So don't ask any questions. So do you have a question? It's not quasi-local. It has these processes. These processes are happening at some non-zero rate. They're not exponentially small, and so it's not. Except if this is but it's not just take the logarithm. You got to take the logarithm, and then for every term, you got to get the how many 2 times. Like the logarithm. Can't say, oh, there's infinite number of logarithms. This I can say how. We have we have the usual discussion of pre-thermal time routine. Exists. Small enough. That's the heating rate. And if gamma is small enough, the system can thermalize to that energy very accurately, and then the temperature will just very slowly drift upward. And that's the pre-thermal, where that drift of the temperature is small on the time scale where the system thermalizes. That's the pre-thermal. Now, I'm not talking, I'm talking about thermalization, so now I'm talking about infinite. Different primary is really not asked about. So we have, roughly speaking, 3 regimes of and what we're doing is we're doing finite and say regimes, not phases, finite omega of Mars. In order, so typically gamma goes in minus omega over omega. So in order to get small, really for large n, you got to go to thinking of that regime, and then we can also the interesting limits for what I'm talking about are n and omega to infinity together in certain. But I'm more interested in finite and finite omega because laboratory. Okay, so is might not be right. So I'm assuming the derived couples to the whole system, And this N is just because the process that absorbs the photon can happen anywhere. Now you could have to drive up only one degree of freedom in the system, and then you won't have this N. So this is sort of optional. If omega is large, J is the microscopic energy scale in the system. And flipping that spin is only going to give you an energy J. So in order to absorb a photon, you got to flip omega over J spin. And that's a process that order omega over J in perturbation theory. It's the same argument all along, right? It's ordered omega over J in perturbation theory, so therefore it's actually. This is something that certain context that this paper obviously looks at what they call some aspects of that. Some yeah, I will. Yeah, no. C1 is no. And this is when with no heating, that's when you can take the logarithm, and this is equal to this, and this is quasi-local. And so you do have an extensive external. So this is something that's the regime you want to be in if you're close to the end. You can really get into this regime. That's now going to heating very slow. That's heating really zero. That's okay. And in some sense, this is the pre-thermal time regime extending all the way out. Basically, this and this is the same eigenstate. Energy. So basically, this regime is when the matrix element, again, the matrix element for effective those two. Effective omega is less than any body level spacing of the system. Right? So the idea here is, here we are at this energy of have an effect as an eigenenergy. We're in this eigenenergy, and then go on to the effective plus omega. If I were to absorb a photon, I would be up here, right? Sort of broken scale here. But up here, there's an eigenstate here, there's an eigenstate here, eigenstate here, eigenstate here. And the closest eigenstate is typically far away from the matrix element, so it's often down and it doesn't. And if you take, right, so you get into this regime for finite systems, and there's a certain age of limit, so you're in this regime. This process doesn't happen, even though there are states near the effective plus omega, they're all oscillating. Except occasionally there might be one where it happens to be nearby and you get arrested. And so there will be a pair of eigenstates resonating, but they're exponentially rare. So the system is keeping up. One eigenstate happens. Seeing something peculiar and we figured it out. So those are okay in no large system. A few eigenstates might be, they're not really eating, they're just sort of Rabi oscillating back and forth like this, right? But then it's not really, right? It's only heating if this really gets absorbed. That's regime. See, so regime 3 is gamma is much bigger than omega. Here, this is the regime everybody talks about for heating, so heat's and if you drive the whole system because of this factor in here, even if you keep omega fixed, you take the limit of an infinite system, eventually it's going to get bigger than it. So if you drive only one site, you don't necessarily end up. Okay, so it heats to infinite temperature, and the energy, because gamma is much bigger than omega, right, so this is the process of absorbing. Basically, the energy is only given served to this precision. Just putting that decays at rate omega, the energy is only served to that. Right, and so it heats up to infinite temperature, and infinite. It's really infinite temperature in that all states reach. This is the standard picture of Floquet heating, the ultimate thermalization. But there's an intermediate state. When I talk about T2, you will see. Basically, omega over n. And then each of these regimes you can add, if I wanted to n to infinity and omega to infinity, how do I do it to end up in that regime? And the distinction between regime 1 and regime 2 actually gets sharp. So it's sort of like a phase, but it's really just a crossover that happens sharp. There's no critical phenomenon. Transition sort of. It gets sharp, but it's really a smooth thing in the critical. Regime 2 is when we're not in regime 1, and we're not. And this is, so regime 1 is very high frequency, regime 3 is low frequency, and regime 2 is. And now, what's going on in regime 3? The essence of it is this: E effective is conserved modulo omega through division gamma. So this is your conservation. Kind of an unusual conservation law. Exact, right? But if and obviously if we're in regime 3 and this is much bigger than this, being considered modulo omega to a precision that's much higher than omega means it's a meaningless statement. But when this is small, much smaller than omega, then gamma. When gamma is much smaller than omega, high precision is small precision. Small precision is high. Right, and so this gives a a regime where the system thermalizes with these constraints, it does heat, but the distribution it ends up in is not infinite temperature. What it looks like is this. So here's the energy. Here's the energy of infinite temperature. Effective infinity. And an interesting case is when this is half, right? So this is a, well, let me just go. You're gonna have something like this. So this is now, so one thing you can do is you can say, what is the distribution of the energy in an eigenstate of Floquet? Now in regime 1, it's a delta function at one end, because the eigenstates of a effective and Floquet operator. In regime 3, it's just a Gaussian distribution around infinite temperature, because it heats up to infinite temperature and equally populates all states. But in regime 2, it looks like this, at least for some cases. These are spaced by omega, and they have width. And that's the thermal equilibrium distribution in regime. My initial condition is a probability distribution of the energy. Well, okay, so what I need to do. So we need, in order to thermalize to something like this, need an initial state with delta less than omega. So the uncertainty in the initial energy is less than omega. Now, if it's less than gamma, broaden with gamma. But if it's broader than gamma, that will stay. So this width here of the final state, this is for an eigenstate. So I started with delta E effective equals 0, and it broadened gamma because it absorbed these photons and typical line width of a process like that. But if I start with a delta E bigger than gamma, it just won't broaden. It'll absorb photons, but you just get these, and the width of this will be set by the initial state, not by gamma. So this is the larger of gamma or the width of the initial. And so this is it's not an infinite temperature ensemble. The mean energy is infinite temperature. So if you just look at the mean energy, it's heating to infinite. But it's a different distribution. And then if you're dealing with a small system, you can set it up so this peak and this peak are noticeably away from infinite temperature. So this is positive temperature. The temperature has this annoying feature that as you go to higher energy, it goes up to infinity, and then it goes back to minus infinity, and then it becomes negative when it's higher than positive. So the negative temperature, these peaks are negative temperatures, these are positive. So it heats up to, so this is the thermal equilibrium state. It's a new kind of statistical mechanical ensemble for Floquet systems, which has, so you can just say, let's maximize the entropy given this. That's a kind of ensemble. And that's what Floquet system in regime 2, a new ensemble for this. And if these, right, you can get into a regime. So we made some models, all-to-all interact, basically the Sherrington-Kirkpatrick transverse field Ising model, and tune the 20 spins and tune them. And then we prepared an initial state, which was sort of realistic in a quantum simulator. And this can happen on a time scale of just 100 Floquet times. So this is something that it's not very far from feasible with current devices. Although when we talk to I sell to people, they say, "Oh, you just 1 order of magnitude past where we're today." So I think this is something that very soon someone will be able to do this in the laboratory. And what's kind of cool about it is like you can start here, you can start with a state with no weight over here, and it's got a definite energy and temperature. And then what it does, it becomes a statistical superposition of having absorbed one photon and not having absorbed one photon. And you can get it into a regime where these are really observably different. So it sort of spontaneously goes from a non-Schrödinger cat probability distribution to a Schrödinger cat-like probability. But I'm saying this probability distribution, I'm not saying state. There's no interesting appearance between this because it's really thermal. But having something sort of spontaneously break up the probability distribution in an equilibrium that breaks up into two terms, that's kind of so if you wanted to ask, what's a version of this? So the Boltzmann distribution is e to the minus beta h. Say for the Boltzmann distribution here, a Boltzmann distribution here, e to the plus beta h. So an approximation to this, string these two p, is a Boltzmann distribution given by this, cosh. So if your Boltzmann factors were cosh beta, that's the canonical distribution for this. I'm drawing you the micro. The canonical distribution would be this. Here. Yeah, this would just capture these. You do, of course, we could make a function that capture the rest of it. But basically, what happens is, these peaks are stronger than these because the entropy here is higher than here, right? Entropy is highest here, but we're not allowed to go there. Here, the entropy is highest. I've done the symmetric case, right? If I make it off center, then the peak that's closest to infinite temperature will be high, and the one that's farther will be the lower, because the one that's closest to infinite temperature has more states. And then this is smaller just because the density of states is lower over here and lower than the peak of states. Smaller if we have it. Typically, what happens is when we get into this regime model, we could actually build the edge of the spectrum might be here. We might just have 4 peaks, and then we hit the edge of the spectrum. This is the ground. This is the ground state. This is the highest excited state. This is this equilibrium. Infinite. You really need omega to be able to order the full. Okay, that's the end of my 4 lectures. On a class. Any questions? I think I'll hand over there. Yeah. Yeah. The thing is, this process happens at rate gamma, and the resulting peak is of width, right? So I don't know that. I haven't really thought about that, whether there'd be an interesting transient going to be, or maybe you could have a situation where. Right, of course, there's a standard pre-thermalization where it's at early times it looks like this, no heating, and then at later times it heats and it would go to back, or it might go to this, depending upon. Right, so standard pre-thermalization is it looks like regime 1 in the pre-thermal time regime, and then at later time it either goes to regime 2 or regime. No, not in the ordinary thermodynamic. The ordinary thermodynamic limit. If I just drive one site, yeah, maybe you could. Yeah, if you drive just one site, you probably get to regime 2 in the standard. if this formula. Right, you know, there's actually sometimes some logarithms up here, right, and that. That, yeah, good question. I haven't really thought it through. Yeah, he might answer it. So that says you vary n. But what if you fix n and vary time? Would you ever have that sequence? I think that's what Charlie was asking. Yeah. 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 So probably, yeah, there's enough creativity and thinking about it, you can probably get it to do that. I haven't really thought. No? Good. Hand up, Leo. No, but that could be true in all regimes. Because we're comparing, what do we? Well, I guess. Right. Comparing to this isn't really about that. That's the possible n in front of it. Right. So you can be high order in perturbation theory and have this be here or have it be over here. Yeah, I guess if you're only driving one thing, then maybe that's right. That if it's high order, if it's only a high order process, maybe you're necessarily like, although I don't want to insist on it, but yeah, that seems. These are all. Yeah. You want something more microscopic. Yeah. Yeah, when we're in the regime where this is an issue, it's always where the process of the heating is a high order. It's slow, right? If it wasn't slow, it wouldn't be an issue. You'd be right. And so it's always all this discussion is in a regime where omega is much bigger than J. So it's a high order process, and that's why it's slow, and that's why this is an issue. That's why, or regime 1 or 2, they can only exist if you have this. So you're sort of automatically in that regime if you're having a discussion. But then once you're in this regime, it doesn't guarantee, you could still be in regime 3. And then it's a quantitative thing of calculating this. We know it's going to be exponentially small in this ratio, but there's 3 factors, constants up in the exponent, and then you need to compare it to the, right? And this is exponentially small in n. I'd like to have an experiment that we initialize it with a probability distribution like this, and it goes to equilibrium, and the probability distribution breaks up into 2. So it spontaneously does, and that's what happens in this simple model that Alan designed. And it's happening, with just we deliberately designed it in ways that it seemed like it's not beyond what present capabilities are. So an initial state that's easy to prepare has narrow. The meeting happens on a time scale that just 100 or 1,000 Floquet cycles. It's not some long time. And the idea is this. And if you could, right, and then we had, you weren't actually measuring E effective, you were measuring something that's easy to observe that has a lot of overlap with E effective. So there was some extra broadening associated with that, and you're not really looking at E effective, but still you can see. So we were trying to keep it as realistic as possible. And, it actually worked easier than I thought. I thought if we really made all these things super realistic, it would make it really hard. It wasn't that hard. But it still seems to be too hard for the various people. Could possibly do those experiments. I guess I spared you guys my rant about quantum. Like, I think I've never said it. I said I did it at Soda. But I think I haven't said it this at all. Well, it's like 5 minutes into coffee break. So, Anisha, you're one of the organizers. And she's heard the rant. And do you want to have coffee break now? No, I don't. No, I don't.